Howdy, AP PreCal. It is Miss Kosh. Today I want to work through Mr. Passwater's notes on section 1.4. I might be teaching it slightly differently in my classroom, but this is good stuff. Okay, so they're telling us a polynomial function is any function representation equivalent to the analytical form, where we have typically this a sub n is a value, a number. A sub 1 is a real number for each I. Oh, they're defining it to be a real number. That's interesting. Huh, okay, I don't know that. For our purposes, polynomial functions will have real coefficients, but I don't know that they have to be. I'm gonna do some research. That's interesting. Okay, and so basically, you've got each coefficient is corresponding, like they write it this way, like this is coefficient, well, your constant is a sub 0, your first, or the term that's got x to the 1 would be like a sub 1 would be your coefficient, and they just like to get this in a fancy way. And so this subscript matches with the exponent. Okay, so the leading term here is that a sub n, whatever that value is. The degree is n because that's the largest degree that we have. Leading term. Oh, the whole term. Okay, my bad. Is a sub n times x to the n, and then my leading coefficient is a sub n. Okay. On this one, the leading coefficient, I see 3 terms. The largest degree is 4, and the degree and the leading coefficient is 3. On this one, they switch the order around just to make sure you're paying attention. The leading coefficient is -7. The degree is 3. On this one, the leading coefficient is 4. The degree is 0. I mean, it's a very boring polynomial, but it is a polynomial. I keep bleeding through. Let me not do that. Okay, so the extrema of the graph are the minimums and maximums. There are 2 types of extrema. We could have relative or local, absolute or global. I tend to use all 4 words. So this has a local minimum at, well, we have a local minimum here at x equals 0. And then we have a local maximum at x equals, I see one at -2, and another one here at +3. This is also an absolute. It has an absolute minimum, an absolute maximum value of 2 at x equals 3. And notice so nicely, it might be hard to see in the video, this has an arrow, this has a dot. That's a point. So its absolute minimum, it could be at the top, like where it changes from increasing to decreasing. But this absolute minimum is where the graph stops. And so its absolute minimum is -3, and that happened at x equals -4. I didn't talk about that in my notes. I probably should have. Anyway, endpoints are things that we should consider with local max and mins also. Okie dokie. So then he says, find and classify. These are both arrows. Relative minimum. I don't see one. Relative, none. Oh, NA is what he tells us to do. Okay, relative maximum happens at x equals 1. Absolute minimum, NA. Absolute maximum it equals 3 when x equals 1. Okay, so this next one here, we have this is an endpoint, and this one keeps going. So good job for him doing that. I should have done that. Relative minimum, I have a relative minimum here when x is equal to -2, a relative maximum. I have a relative maximum at x equals -4. I would also argue we have a relative maximum at 3, but it is an absolute maximum. Wrong spot. Absolute maximum when x equals 3, and that was a value of 2. And we have no absolute minimum because we keep going forever and ever and ever. Did I consider everything? So NA. We had a relative maximum at I would also, let's go ahead and put 3 there. Okay, I think that's correct. If not, comment below, but say something nice. Okay, relative minimum. So once again, here we have a dot. Oh, we have a dot. Okay, a relative minimum. We have a relative minimum here at -3. That's also an absolute. The absolute minimum is when x is equal to -3. Where was that? It had a y value of -3. The relative maximum, there's a relative maximum here when x equals 0. There's also a relative maximum when x equals 5, but this is better described as an absolute maximum, which was it had a value of 4 at an x value of 5. Hopefully that wasn't too confusing. I'm sorry. Okay, between 2 real zeros of a polynomial, there must be at least one local max or local min. I think on my notes. No, I don't see that page. Oh, here's how I described it. I said between every two distinct real zeros, there's a local extrema. Okay, so at least one local max or a local min. Polynomials of n degree must either have, no, he wants even. Of an even degree must either have an absolute maximum or an absolute min. Absolute max or an absolute minimum. Okay, let's keep going. And then he talks about points of inflection occurs where a function changes from concave up to concave down or concave down to concave up. At a point of inflection, the rate of change of a function changes from increasing to decreasing. So if you remember, the average rate of change, when it's increasing, it's concave up. That looked funny. When it's decreasing, it's concave down. Find the graph, where are any values of x, where g has a point of inflection. I see concave up, it looks like it's changing here, and then it's changing here. So we're concave up, concave down, concave up. I think it's both at x equals plus or minus 1. We won't know how to find them accurately until we get to calculus. Okay, so I would say assume that they're nicely placed on the graph unless we tell you otherwise, or until we teach you calculus. Okay, average rate of change is increasing it from 3 to 4. 3 to 4, my average rate of change, this is concave up, so it's increasing. From -4 to -3, that's concave up, so that's increasing. From -1 to 1, that's concave down, so it's decreasing. From 1 to 2, it's concave up, so that's increasing. Oh, here's a calculator problem. Here we go. I did not type this in ahead of time. I still have the last one from, okay, so menu. I'm going to come to my graphing feature. I am, okay, delete. Let's start over again. I have -1.37x to the 5th power. I haven't done this one yet, y'all, so sorry. If you see me type this in wrong, comment below. I'm good, but I'm not perfect. Minus 0.357x squared. Plus 3. Okay, 1, 2, 3, 4 terms. I think I've got that. I'm going to set my window to be standard just to see if that's a good window for us to live in. Maybe. Okay. Based on at what time does the number of the cars change from increasing to decreasing? Oh, they want us to live between 0 and 3. I'm sorry. Let's go to our window and let's live. I'm going to go a tiny bit smaller than 0, and I'm going to go a tiny bit bigger than 3. And let's make our y values, it may not have been enough. I don't know what the right window is because I haven't looked at this yet, but here we go. Oh, that was interesting. Okay, I was a pretty decent guess. Oh, hang on. Let me change the window a tiny bit. Let's go a little bit higher, 32. Huh, okay, clever. Based on that model, at what time t does the number of cars change from increasing to decreasing? Oh, so we want to know when, hang on, can be modeled by the function. Based on this model, at what time does the number of cars in the parking lot change? Okay, so the number of cars, like, I guess this is all through the night. They don't do a whole lot, but then all of a sudden they really increase until they get to this maximum value. Then the number of cars decreases. So G solve, I'm trying to find the max. And so, well, that's interesting. That's funny because my scale, I couldn't tell that was a maximum. But here we go. Based on this, at what time t does it change from increasing to decreasing? When t is approximately 2.4456. And I think that's all we need. So, all right, like, subscribe, comment, all the things. Bye.